Thank you, Eric. Why don't programs run n times faster if you buy an n-core computer? I mean, a lot of programmers just thought when multicores came along, 4-core computer, I can take my code, run it on this thing, and it'll go 4 times faster. And then they bought these things, and they found it wasn't true. There's a guy called Alex Gunaris, who was the chief. He worked with Bill Gates for years, and he was the chief scientific officer of America Online. And they were building a big thing. And he decided, when the multicores came along, he decided to retool all their machine parks. So they bought these massive multicores. I think he said there were something like 16-core machines. And he put all this, and he did all this, and he put all the software on these 16-core machines and hoped that everything would run 16 times faster. And it didn't. And he was very disappointed. So then he started looking at different technologies and different languages, and everybody promised that you could make things go faster by using different technology. He tried all of these things. None of them worked. And then he tried Erlang, and it worked. Actually, it didn't go 16 times faster. We did it moderately faster without doing that much effort. And so he was quite happy about that. So I want to talk about this and some programming models. And I was very taken by Peter's talk because he said some things which resonated with me, and he used some words there that I thought were very nice. He talked about horrible words, simultaneous and parallel and concurrent, and so he's done a bit of the groundwork for me. Now, what Peter's been trying to do is to climb Everest, because making a concurrent memory model is like climbing Everest, and I'm not that smart, so I don't want to climb Everest. I just want to go up one step there at a time. And so I can answer this question here. Why doesn't my program run faster when I run it on an n-core computer? And that's because to do so, I would have to write a parallel program. And it's difficult to write parallel programs. It's extremely difficult to write parallel programs. When programmers think about parallel programmers, to start with, most programmers don't understand the difference between a parallel and a concurrent program. In one of my books, I spent a long time explaining the difference between concurrency and parallelism. In fact, I had a blog entry called Explain It. I have some entries in my blog called Explain It to a 5-year-old. And there's a very simple example of what parallelism, what concurrent is. Outside, when we have coffee, there are 3 coffee machines. And if you want to serve coffee quickly, you can form 3 queues behind them, and that's parallel. Concurrent would be if you had 1 coffee machine and 3 queues waiting for it, and they very politely interleaved as they were going to get their coffee. So parallel means sort of really simultaneous in the real world, but then that's another horrible word, simultaneous. I used to be a physicist, and did quantum mechanics and stuff. So what does simultaneous mean? Well, we don't really know. We're not talking quantum entanglement and things like that, and spooky action at a distance. If we forget about that kind of stuff and think simultaneous means, it means nothing in physics. There's no such notion. There is the idea of rays of light flying around, and that happened before that. If you you'd have 2 stars explode. If you 2 are stars and you explode at the same time, and I'm standing here, I will say this star exploded first. But if I was standing here, I would say this star exploded first. So this notion of things happening at the same time doesn't exist in physics. And so it's really a very bad idea to base programming models on the idea that you can violate the laws of physics with impunity. If you violate the laws of physics when you build a programming language, things become very difficult. Now, unfortunately, programming languages are divided into 2 categories. There's the shared memory concurrency model, and there's a message passing concurrency model. And the shared memory concurrency model violates the laws of physics big time, and is extremely difficult to understand. And the message passing model also violates some laws of physics, but it violates far fewer laws of physics, so it's much easier to understand. And so it has this property of single sites where things happen. So we don't talk about simultaneity or things like that. We talk about single places which consume streams of events and are quite easy to understand. So there are a lot of languages in this latter category. Virtually all programming languages, C, Python, all these use shared memory concurrency. And concurrency actually isn't in the programming language at all. It's in the operating system, and there's this kind of interface to it. There are one or two languages, Erlang, Alexia, Pony, which use message passing concurrency. And of those, I think Erlang is the only one that's kind of stable, in the sense you can build large products with it. It's been around for a while. So things like WhatsApp, things like Ericsson's, the infrastructure for Ericsson's smart data, things like that are programmed in Erlang. And they work pretty well, and they have billions of users using these things. So programmers, I think they don't understand the difference between concurrent programs and parallel programs. And they don't like to learn new languages, new ways of doing things, because they've invested an awful lot of time in learning how to program in Java or C or C++. And it's extremely difficult to learn well, it's not difficult to learn a new programming language. You can learn a new language in 2 or 3 weeks, I think, the syntax. But it will take you several years to learn the libraries and the programming idioms and the way of thinking. It's changing the way of thinking that's the difficult thing. It's not learning the language. The language is just the syntax. So basically, all those first languages I had up, Java, JavaScript, C, C++, all these things, you don't have to change the way you think. You have to change the curly brackets and put a few semicolons in. There's no difference between Java and JavaScript and Python and Perl. They're all imperative languages, more or less the same constructs, all done more or less badly or well, depending on your point of view. But the way of thinking is the same. And then you have other language families, functional languages, you have logic languages, you have constraint languages. We've actually got to think differently, and that's a barrier to learning. Programmers actually dislike complexity, I think, or at least I, as a programmer, dislike complexity. So I like simple things which I can hopefully understand. And I would actually love to be able to write correct programs. But I've kind of given up the notion of writing correct programs when we write very big programs. So I'm more thinking that if we write big programs, there are just going to be errors in them. These errors are going to occur at runtime, and we have to live with these errors. We have to fix them up and carry on. And those programs have to evolve. I'm not thinking of programs that are put in a machine and you stop the machine and you change it. They will evolve with time and run forever. And there will be lots of errors. So they become more like biological systems, and we need to understand how such systems work. And today, I think we've got into a horrible mess because when I used to work at Ericsson, if you walk around the corridors and you listen to the programmers talking, they're not talking about how to solve their problems. Half of them are talking about how to solve problems with their tools. Well, Git doesn't work, or Jenkins doesn't work, or these things don't work. You say, well, what problem are you solving? What do you mean problem? The problem is Git doesn't work. No. Ericsson doesn't sell knowledge about Git or something. Ericsson makes phones and things like that they sell to people. Right. So we want to make it easy to write parallel programs. Right. We can't. Writing parallel programs is extremely difficult. I would just give up the whole idea that it's easy to write parallel programs. So let's do something different. Let's make it easy to write concurrent programs. We can. We can make it relatively easy to write concurrent programs, although we can't write parallel programs. And then we can automate the parallelization of concurrent programs. And people have tried to do that for years and largely failed. I remember the efforts going on from the 70s to parallelize Fortran. Despite massive efforts, I think they only managed to automatically gain 15% speed-ups, despite throwing massive brain power at the problem. It's an extremely difficult problem. But we can do it with multicores. And how do we do that? Well, instead of letting the computer or some formal system decide the granularity of the concurrency, you let the programmer decide that. Programmers are quite good at that, I think. They just identify what they think are concurrent processes and tell the computer. Don't let an automated system do that. There's never been an automated system that can do that successfully. I think it's quite easy to do it, especially if you're programming something that's modeling the real world. Okay. So the programmer decides the granularity of the concurrency. Yeah. And for real-world problems, often they are parallel to start with. So there's actually not much problem in deciding that granularity. I mean, if you were building a web server for 1 million people, you just make 1 million processes, one process per person. So in fact, it's a slightly different way of viewing things. That concurrency is inherent to the problem, so you just need to mirror it in the architecture of the system. So one point I make, which people don't really understand, is if you program in C or C++ or Java or something like that, and you build a web server for 1 million clients or 1 million sessions, that is one sequential program that's been persuaded to take care of 1 million connections by spawning off threads and doing devious things with shared memory and things like that. The Erlang way of viewing that is it's not one process with 1 million clients using it. It's 1 million parallel processes that know nothing about each other, and each process handles exactly one session. It's much easier to think about it. And ideally, we would put these on completely separated machines. If we put them on physically separated machines, if we have 1 million machines and put one server on each, it's intrinsically parallelizable. So to parallelize things, you need to make them independent. If they are independent, you can horizontally scale them. So the reason you can't make things faster if you have this case of massive parallelization is you can't horizontally scale. And the reason you can't horizontally scale is because you've got shared memory. If you've got pure message passing, you can do that. So the granularity of a lot of problems and how you break things into parallel processes can be done by observing the world for real-world problems. So here's, I don't know if anybody, has anybody seen the video? Yes, very good. So we made a promotional video in 1992 for Erlang. It's got 3 people. It's me and Robert. By that time, the 3 of us working on Erlang, and I say hello, Robert, and Robert says hello, Joe, and then I say hello, Mike. And if you wanted to turn that into some program code, you can just map it. We start here, hello, Robert. So Robert, bang, hello, Robert. Robert receives a message, and then he sends Joe, hello, Joe. Joe receives a message, which is here, says hello, Mike. And we base that on observation. So the code here is pretty much isomorphic to what we have observed. So if we look at this picture and say, so how many processes would we do to model this? The answer is 3. There are 3 people involved. It wouldn't be 5, it wouldn't be 7, it must be 3. In a lot of problems, the mapping of the problem onto the concurrent structure can be done by observation. Right. And this is what Carl Hewitt calls physics modeling. This is in Hewitt's description of the actor model. So one parallel operation in the real world equals one parallel process. Very simple. You just sit there and observe what's going on. And then what do you do? Well, what the Erlang system does is to make that into an efficient program. The programmer does this first step here. Describe the problem as a set of concurrent processes. It's rather easy. Spread the processes over the cores that you've got available to do the job, and then you measure. And is it fast enough? Yep, you're happy. And if it's not fast enough, you've got 2 alternatives. You can manually map the processes over the cores, because you know more about it than anything else. Or you can change the concurrency model, maybe introduce more concurrency, or less, well, help it go. So how do you spread the processes over the cores? Well, that's tricky. That's very, very difficult. And fortunately, all the people who program in Erlang or one of these languages don't need to do that, because there are 2 or 3 people at Ericsson who know how to do that. So instead of having everybody who programs in a language have to do that, it's better that you've got 1 or 2 people who really know how to do that. If you were programming in C++, every single C++ programmer on the planet has to solve this problem, which is an extremely difficult problem, and they'll probably get it wrong. If you're programming in Erlang, Richard Green and a few other people know how to do this, and they know all about spin locks and God knows what. And, oh dear. OTP. This is stands for Open Telecoms Platform, which is the kind of, it's what you get Erlang with. This is done at Ericsson. It's like the difference between Unix and C. You could say that OTP is like Unix and C is like Erlang. So the Erlang programmers, they know nothing about how multi-core processors work. They haven't a clue. And the people who write the schedulers and things like that, 2 or 3 people on the planet know how to spread this over the cores. Now, scheduling is actually a very difficult problem. If you're on the constraints talk Christian gave on Monday, this is an NP hard problem. If you have, it's an AppSec problem. If you want to pack these things into, what have we got here? 10 jobs on 8 processors is 3.7 times 10 to the 16th. It's an NP hard problem. And for any reasonable, there's not enough time in the universe to solve these problems. It's very difficult. So the best thing to do there is not do it this way at all, but make sure that you've got lots of little processes. Packing huge big rocks into containers is very, very difficult. But pouring sand into containers is really easy. So if you think of processors like little grains of sand, and you think of processors like big barrels that you have to fill up, then filling your barrels up with sand, you can pack them very nicely. You just pour them in, and it'll all work. Filling it with huge big rocks isn't going to work. And when we program in C++ or any Unix system, actually, which uses pthreads, it's like packing rocks. Because these are massive, great big, they are the smallest size of a process. What is it? Somebody tell me. 100 kilobytes, 64 kilobytes, something like that. These are big rocks which we can't pack into memory nicely because of the memory management hardware. If you really want very small processors, you can pack them nicely. So how do we make it easy to write parallel programs? Well, don't confuse programmers with a lot of different things. Just have 3 primitives, which are in the language itself and not in the operating system. So the 3 primitives are spawn, which creates a parallel process, send, which sends a message to that process, and receive, which receives a message. A receive is a pattern matching operation. And in fact, you don't send it to the process. You can think of a process as something that's got a little mailbox, and you can think of messages as items of mail. And the send operation is the postman who sends a message and pops it in the mailbox. And the receive operation is somebody walking to the mailbox and sort of leafing through it and pulling out what they want and then going and do something. When they've done that, they go back to their little mailbox, sort of open it up and see if there's anything to do. And it's all very nice because the process that's doing that is purely sequential. And we understand sequential programs much better than we understand parallel programs. When we implement this, the Erlang virtual machine compiles this down to single instruction. It was originally a bytecode interpreter. Now it's a word interpreter. But these are single instructions. Send, spawn, and receive were in my original Erlang single bytes. The hardware people didn't make those instructions. They made completely different instructions, loads and stores and moves and tests. And they have all these instructions that I don't want, and they don't have the instructions I do want. So when you're designing a high-level language, you say, oh, well, I don't care what instructions the machine's got, because these are far too complicated for me to understand. I will invent an instruction set, which makes it easy to make my high-level language. So, for example, if you look at the JVM, it's a simple stack machine. It's got almost the same architecture as the .NET machine. It's just a simple push and pop stack machine, very easy to understand. And they all go back to Viet's P-code machine, just a simple stack machine with pushes and pops on. And then what you do is you emulate that in a C program. And people like Christian with his nice compiler projects work out how to map the instructions that you didn't want. Sorry, they work out how to map the instructions that you did want onto the instructions that you didn't want, because the instructions that you didn't want are the ones that the hardware people have given you, because they never talk to the high-level programming language designers. If they did, they would be like Charles Moore and make the fourth chip that's got the instructions that you do want. Right. So Erlang doesn't have any of these. It doesn't have shared memory and semaphores and mutexes and monitors and spin locks and critical regions and futures and thread safety and all these horrible things which are incredibly difficult to get right. Just make life easy by having pure message passing. We just send messages. They're copied in their entirety with no messing around with pointers. You either get the entire message or you don't. The failure semantics are the same as in the real world. If you send a message to somebody, it either gets there or it doesn't, and you'll never know, which is just like the world behaves. So you have to ask ourselves, why do we do pure message passing? Oh, and isolation. These things have got to be isolated as well. Well, actually, there's one programming model now. One thing that I've always thought is kind of crazy is that we have different ways of programming systems depending on the scale of the system. So if you're programming an application on a single core machine, on one computer, you program it one way. And then as your problem gets more complex, maybe you exceed the capacity of this single computer and you want to program it on 2 or 3 computers instead of one, and suddenly the entire programming model degenerates. You've written it in such a way that you can't run it on 2 computers. So the way we start to write a lot of programs is, first of all, we write them on one computer. Maybe the capacity of that computer isn't enough, and we buy a more and more powerful computer, and we scale it up, and we scale it up. And then one day, suddenly we can't do it anymore on the one computer. We need to use 2 computers. But suddenly we can't run our program on 2 computers because we've written it in such a way that we can only run it on one computer. But if we had written it from the beginning using message passing between isolated components on the single computer, then when we put it on multiple computers, it's going to scale nicely. So I really don't want to program these different things in different ways. I don't want to program this in, well, here's a nice, you showed this very beautiful diagram. The way we program that writing a small program and then looking at the architectural things I have to do to turn it into a big program, I would suggest we should start by writing a big program and then scale it down to the case of a small program. So if you were going to, imagine you're going to write a sort of webby sort of service or a Internet of Things thing or one of these things. There would be 2 ways of doing it. One is you could say, well, what should I dimension this system for? Well, you say, 100 users or something. You make it for 100 users. And then you deploy this thing and you find we've got 1,000 users. So you have to then start scaling this thing up. And that can be very difficult. I would suggest it's much better to start saying, so how many users can we have? Well, I don't know. I usually say, start with 10 to the 50 users, because there are 10 to the 50 atoms on the planet. And we say, OK, so let's assume that every atom wants its own web server or whatever. And so we make the address space to work for 10, or you might do it for the entire universe, but that's daft. But you start off with some unreasonably large number. And then you make your architecture to work for that. And then it's going to be, and then you scale it down to your 10 users. And it's still going to work for 10 users because you've dimensioned it to work for 10 to the 50 users. And you scale it down to 10 users, and it works very nicely. Of course, that will be less efficient than somebody who started with the problem, say, I will make a system that handles 10 users. Oops, what happened? I pressed the button by accident. Oh, goodness. Sorry. So when you're showing off this stuff, the Erlang stuff, contra the C++ stuff, the first reaction that people will say is, yeah, but my C++ thing is 5 times faster, or 10 times faster, or 30 times faster than the Erlang thing. And I said, yes, but you're only doing it in a domain that's unscaled. When you go into this big domain, you will see an opposite effect. And that appears to be true. Basically, because you can't build very big systems in C++, because you have to start addressing the same problems that we have addressed in Erlang. So, for example, if you deploy a system with billions of users over a long time scale, it's going to be impossible to keep it consistent. You can't change the software by stopping the system, changing all the software and restarting it. You have to live with evolution. You have to live with errors. Errors will occur. We're moving to an age where we'll have light-emitting diodes sending messages to each other, Li-Fi going at 10, 20 gigabits per second. In each light bulb, there will be a processor that's probably 100 Cray-1s, computational equivalence. And we will build this massive, super-duper message-passing supercomputer, which can do anything we feel like. And then we've just got to kind of think of something. Nobody can actually think of anything useful to do with this, so we can remotely control a kettle or something like that. But we've got this fantastic structure. We want to program it the same way, in a scalable way. So with pure message passing, we can handle failure. I'll talk more about that later, because I've got some separate slides about that. So the details. How did the original Erlang work? Made a good design decision around about a long time ago, about 1989 or something like that, and was every process should have its own stack and heap, and there should be no shared anything, no shared garbage collection, no shared anything at all. That turned out to be a very good decision. Strange enough, Robert and I, who were then working on Erlang, always believed that one day somebody would come with an application where we needed shared memory. And what we would do when that day came, well, if they came to us and said, well, we really need shared memory because it's not efficient enough, then our strategy, we'll rewrite it our way, and hopefully it'll work. And if it doesn't work, then we will give in and do some shared memory. And we never did. It never happened. Oh, well, it's not quite true. Erlang's got ETS tables for building massive databases. Because you don't really want to copy the entire universe if you've got a database representing the entire universe and you change something in it. Well, you can't make another, the universe is everything, so you can't have like two well, unless you believe in brain universes, but we couldn't access them anyway. So the original reason for this has got nothing to do with scalability, and has got nothing to do with performance. It has to do with fault tolerance. And the problem with shared memory is not, Peter suggested the problems with proving or demonstrating what would happen when you go into a critical region. My problem with shared memory is not so much that you can't correctly lock things and go into critical regions. It's what happens if a program is in the critical region and crashes. Because it's changed the memory in some way, and then it crashes. Well, sure, a monitor can detect this fact. And it can tell the other process, okay, so now it gets removed from the critical region. The second process comes along and says, oh yeah, but what happened to that other process? Well, people like Eric say, oh, well, we've got transaction memories for that. Oh, that's great, that will solve your problem. Yes, but it doesn't solve it at scale, it solves it locally. So I've still got that problem at scale when I've got something in Sweden talking to something in America. Where do I put the shared memory? I mean, do I put it on a submarine in the middle of the Atlantic? Or it doesn't exist. It's two different memories talking to each other. So failure. Failure is difficult to do. Failure, you have to ask yourself, what happens, how do I write fault-tolerant software? What happens if the entire computer crashes? I'm not talking about divide by zero in a thread. I'm talking about the entire computer crashing. Well, you need two computers, or more than 2 computers if you want to be very fault tolerant. And so if you just take 2 computers, let one computer take over if the other fails, and so on, they can fix up the errors for each other. If you think about that, it's impossible if there's shared memory. If there are dangling pointers onto the remote machines, you can't do that. But if you've got pure message pass, you just send everything over in messages. You can handle failure. You just make sure that what you send to the other machines is sufficient to recover from if a failure should occur, and you monitor what's going on. SMP Erlang, this came a little bit later. Now we actually had physically separated cores. And so basically the same model that ran on a single core was now running on a multi-core type architecture, parallel processor architecture. And there's some special things called schedulers, and their job is to move the processes between the cores at regular intervals. So they interrupt the system now and then and move the processes and tinker around with these things. And hopefully, if they've done a good job, you spend a small amount of time in. Oops, I need to stand here to point this. You spend a small amount of time here and a large amount of time here, and you're monitoring what's going on and moving things around. The goal, actually, it's a slide later, but the goal in the Erlang system is that if you have written your application with a reasonable balance of processes, and you have n cores, that it would speed up by 0.75 times n without you doing anything. So that would mean that if you have a 100-core computer, hopefully it will go 75 times faster without you doing anything to the program. And that's almost equivalent to saying, well, let's say that 25% of the work is going to be done in this horrible bit where you're actually deciding to move things around. Do you remember the earlier slide when I said you can pin processes? That's where you say, well, because I know how my problem works, I'll actually stick these things on this core, and I won't use the scheduler to move them around. I'll tell it. And it's been speculated, although it hasn't been demonstrated, that, some of the network on chip architectures, it would be sensible to do things like TCP, things on the chips, on the edge of the chip, and then put the database in the middle of the chip or something like that and sort of move them in and actually pin them to the right cores. Because there are memory issues and there are propagation delays and you've got to go through cores and things like that. It's not really a good idea to do that, because then you, by pinning things onto cores and things, you haven't made your software future-proof. So when a new architecture comes along, you can forget about that and you'll have to redo it. So it's better just to let the system do that for you. Right. So Erlang is just, here's some CPUs, 5 CPUs. Each one's got its own memory. And these little colored regions, they're the shared memory. And then there's some sort of tree of locks and things. I won't bore you with the details, but they're kind of complicated. So what does this migration logic, what does it do? It does load balancing, process migration, schedules inter-process message passing. And the goal of all of that is to make a small core that can move things around, and that it's non-locking and as much as is possible. So once we've isolated the computations, put them on separate cores on separate physical computers, we get 4 additional benefits. The first benefit is reliability, because if the probability of failure in a given time for one computer is 10 to the minus 3, then if you have 2, the probability they both fail in the same time interval is 10 to the minus 6. So if you want 100 nines reliability, you just get 34 computers and get them all do it in parallel. It's really easy. But the key to all of this is independence. You really do have completely isolated computations. In fact, at that level of reliability, you also need isolated power supplies and everything else, because the planet's power supplies aren't going to be 10 to the 99, reliable. They're going to fail every million years or something. So scalability. We can easily scale horizontally if all the processes are independent. And we can use that to solve massively parallel problems. Now, massively parallel problems are extremely common. the World Wide Web, the internet, is a massively parallel problem. It's, in its nature, has 2 billion people talking to each other, and I think Ericsson says there'll be 50 billion connected devices all sort of chatting to each other. So we do have 50 billion things just all going on at the same time. So it is already parallel, it is already distributed, and it is already sending messages. The daft thing is we're programming it in languages which are semantically completely different to that, which is not a good idea at all. Makes it artificially difficult. We also, by isolating things and using message passing, we make them simpler. Because it's easier to understand small things that exchange messages than it is to understand big things that don't exchange messages. And the reason is pretty simple. If you have a black box and you want to understand the behavior of what's going on inside the black box, all you need to do is observe the inputs and outputs and tie them down and write down some equations and some reasoning about what's going on inside the black box. And of all the principles of computer science, I think my favorite one is this principle of observational equivalence, that two systems are equivalent if you cannot distinguish them on a basis of observing the messages that go in and out. It doesn't matter how you program the inside of the black box. You can program it in Fortran or COBOL or JavaScript or C++ or anything else. It's totally irrelevant, provided it behaves the same way. That's very nice, because describing what's going on in the interface is considerably easier than describing what's happening on the inside. And of course, if we were to open up this thing, it should be compositional. Right. So inside this black box, we should find more black boxes. And we would recursively describe the system. And it becomes compositional. And we can immediately see, if we want to do that in hardware or software, that at every level of abstraction, that's saying, well, okay, so I need 3 parallel processes at this level of abstraction to model this and to write the program. Right. Now, all these things are just communicating with messages. This is actually how we build hardware. We get chips. They all run in parallel. They're all clocked, and they all run in parallel. We connect them, we wire them up together, and it all works. This is not how most people make software. It's how I'd make software. I'd make it that way. Just make these processes. They're more or less like chips. You just wire them up together, and it just works. It's very nice. Another benefit of doing it this way, of sending messages and things, is we obey the laws of physics. I used to be a physicist, so I like that. So I'm saying we obey the laws of physics. So what laws of physics are we obeying? Well, the first one is that messages propagate at or less than the speed of light, unless we believe in quantum. Anybody do Bell's experiment yesterday? I did. No? Nobody? All asleep? Oh, it's good fun. There's a big, massive experiment of Bell's hypothesis to see if quantum entanglement works. It was done yesterday, all over the world. I participated in it by hitting noughts and ones on my computer at random. Causality. This is a nice principle. If B depends upon the state of A and A or B are separate in space, then you must send a message to B before B can do anything. You can't do anything until you've got some information that has changed. Another law of physics, simultaneity in 2 different places in the universe is impossible. We can only talk about simultaneous things when we're at the same point in space-time. And there's a deal of confusion about this. Most of the problems in... I say for a computation to take place, the program and the data have to be at the same point in space-time. If they're in different points in space-time, you can't perform the computation. So you've either got to move the data to the program, or you've got to move the program to the data, or can move both of them to somewhere in between. What we conventionally do is we move the data to the program, which is why we have huge big server farms. We don't move the program to the data. It's absolutely stupid, because all of this costs energy, and it's actually daft sending gigabytes of data to a data center to be analyzed when the program that analyzes it may be a few kilobytes. Much more sensible to send the program to the data. Or it might be even more sensible to send them both somewhere in between to optimize latency or security or whatever you want. The other disadvantage of sending data to somebody's server is you have to reveal your data to not only the people who are analyzing it, but to all the security agencies in the world who will have a quick peep at it to see what it is at the same time. But if they send you the analysis program, you don't need to reveal your data to anybody. So it's much more sensible to keep your data to yourself and ask for the programs from the servers, not the other way around. It also avoids the problem of being blackmailed by Apple and Google and all these who will store all your images in the cloud somewhere and then charge you $100 a year in order not to delete them. And of course, message passing. Oh, I should say that we only have to make this point because people don't understand that. We don't really understand how things are now. We understand how they were the last time somebody told us. So I don't know if my wife is healthy and in good health and everything. But the last time I saw her, she was. I mean, she might be dead. I don't know. But I'm living in this illusion that she's quite happy and working away at the bank at the moment. But of course, she might be dead. But since I don't know that fact, I'm perfectly happy. Don't think she's dead. I would have to leave the lecture rather rapidly if I got a call. And of course, Alan Kay, who coined this term, object-oriented programming, I like this mail. I talked to him a couple of weeks ago. I interviewed him, and we were in great agreement that the big idea of object-oriented programming was messaging. And this it's not about abstract data types and classes and methods and all this horrible structure. It's about messaging. And the one thing that object-oriented languages like Java and C++ don't do is messaging, which is rather strange. Which is why I tell people that Erlang is the only object-oriented language there is, because it does messaging properly. Right. Does all this work? Yes. Well, I mean, it's a good question. Yeah. So when I was working at Ericsson, you say, well, did you have to change the original design to make your program go faster? If they say no, it just went faster, then I would say it does work. I was at one meeting where we had a Tylera 64 computer, 64-core machine, and had done, I can't remember the application, SIP-stack or something on it. And we had this meeting, and I said, the student had done this thing, and it went 33 times faster on a 64-core machine without them changing the software at all. And the management were not very pleased. They were going, why doesn't it go 64 times faster? You've got a 64-core machine. And then I said, well, are you pleased that it goes 33 times faster, or unhappy that it doesn't go 64 times faster? And they said, well, we're unhappy that it doesn't go 64 times faster. And I said, well, just remind me, that other project that was doing the C++, how much faster does it go? And they said, well, it's still stuck at 1. It doesn't go any faster at all. So I think we did achieve a small goal there. And our goal was, I said that earlier, to go 0.75 times faster. If you've got the right concurrency model and written your program in a reasonable way, but that responsibility is the programmer. There's no automatic system that can do that for you. You have to look at it, figure out what concurrency you need. Does all of this work? Yeah, well, it works for things like WhatsApp, Klarna in Sweden, Ericsson. I've just added, I was in China. I was very fortunate to be invited to China last week and learned that Alibaba, which they say is the biggest website in the world, uses a lot of Erlang to do it. And I went to a company called EasyMob, which is sort of the Chinese WhatsApp. I was very surprised when they invited me there. And yeah, it works for that kind of. It doesn't work for. I mean, I know your talk a couple of years ago. Like super ways of inverting matrices and things by sort of jiggling around and working out the time slots. It doesn't work for that kind of stuff. But most people don't want to, well, I don't know. I was going to say most programmers don't want to invert matrices and things. And anyway, they'll use a library to do it if they want to jiggle around fast. But they want to write these funny web things. So does it scale nicely? Well, here's WhatsApp. This was a presentation given in, I can't remember the year. It says 2012. It shows the scaling of WhatsApp. WhatsApp's written in, or the server's written in Erlang. And they were quite pleased about this. Scales nicely. And then last week I learnt this guy from EasyMob showed a slide because they had an Erlang afternoon in Beijing, and I was there. And this is a sort of a company I'd never heard of. I think they consider themselves to be the Chinese WhatsApp. But they don't do a service to the end users. They do this thing here. They provide a platform, which is written in Erlang, to connect apps together. And there's a paid service and a free tier. And in China, 82,149 apps are written using this backend. And I thought, no, 89,000 users, no, 89,000 apps. And those apps are serving over 1 billion users. So they're kind of in this WhatsApp space, and it's scaling quite nicely. So at this stage, I think we should say, well, where are we going and what problems ought we to solve? Alan Kay says we should just throw all this stuff away and start again from scratch. I think if we were to do that, we would not make the mistakes we've made in the past. Well, one of the things you didn't say is, why don't you just sort of throw all this stuff away and do it properly? Or, well, we can't do it properly. We could make another attempt at doing so. We've now got supercomputers absolutely everywhere, and we're loading them down with legacy software, which is probably buggy and incorrect, and we haven't a clue what it does or how it works. It was written with specs that nobody can understand, and it's a complete mess. So what are the big problems? Well, we want to minimize energy. We want to store stuff forever. Well, not forever, until the sun becomes a red giant. We certainly don't want to lose our history by putting everything into the cloud. It'd be rather tragic in 200 or 300 years if we were to go back and say, well, where's all this stuff? And they said, well, sorry, we put it in the cloud. And I was minded of Peter's response. I gave a talk at Facebook, and I met a high-up I think it was a technical chief at Facebook. And I said, so what happens to all our pictures and stuff that we take when we're dead? How are we going to find, people are going to find, our relatives and things are going to find this in 200 years' time? And he said, that's a very good question. And they didn't have an answer to it, actually. So I'm kind of worried that we will lose all of history. So we've got to figure out a way of storing it for a while. Security, we need to figure out how to make these systems secure. The system at the moment is very brittle. If people, it's attackable. If the attack rate is higher than the repair rate, we could destroy the entire internet. So these people who've installed Trojans in light bulbs and fridges and irons and dog feeding devices, once they've taken control of those things, I don't know if you can get control back, because there doesn't appear to be an upgrading mechanism for very cheap devices. So once these things have been pirated, they're pirated forever. If they can put new stuff in and attack it quicker, then we can knock these things out. We could potentially knock out the entire internet, and then you'd have to close off whole bits of it and quarantine it. It would be like the Black Death. It would cause millions of deaths, and the only way to do it would be to quarantine it and rebuild up something from scratch. This is a real problem, actually. We need to figure out how to make systems that evolve, and we need privacy. And then, because all these things are removing jobs, we need economic models that take into account the fact that we can do a lot of things with computers instead of people. Right, so what do we want? What would I like the hardware people to do? I would like hardware these things that are a single byte in my language or a single instruction, I would like them to do that in hardware. So I'd like asynchronous message passing. I'd like all the parsing of the messages to be done in hardware. That's where most of the time goes. Just put some FPGAs or some VLSI to parse JSON or XML or whatever the crap is that you send in. Don't do it in software at all. Do the message queues in hardware. Do the failure detection in hardware. Do some secure data lockers in hardware. Give me cryptographic checksums in hardware, and small CPUs with lots of instruction, with a few instructions. I don't need 10 instructions will do. I don't need lots. I need actually a bit of memory, quite a few megabytes. And I'm sure Peter would be happy if we just had machines with 10 instructions. It would make life a lot easier for everybody. We want low power. We want session types and things to describe the boundaries of what's going on. We need evolution mechanisms so we can run systems forever and they will just grow and we can change them in time. And we need, together with security, as they evolve, we need to make all this secure. So I think that's leaves 5 minutes for questions. I think Eric was, that meant 5 minutes, I believe.
So any questions? I know there is one up there, but do we have any from the floor?
Hello.
Peter.
So the message passing abstraction is a very attractive one. It's a very clean one. But I'm forever struck by the fact that our systems actually end up being a stack of alternations. We have hardware which is implemented with message passing interconnects on which the architects build shared memory abstractions, on which you build message passing abstractions, on which presumably other people build distributed shared memory abstractions. So I can't see either of these as more fundamental. So if you're building these large systems above a message passing base, I imagine, but I ask you, whether in fact you've pushed a whole bunch of complexity into the distributed protocols. And I've written some pretty hairy distributed protocols. They weren't easy to understand just by virtue of being written in messages, and their failure behavior is not necessarily easy to understand. So what do people end up actually building
I think
when they're doing these big things?
The problem with things that are based on message passing is, yes, you do want shared memory to some extent, and then you get into one or two basic abstractions you need to build on top of that. For example, leadership election is one of these critical abstractions you need to do. That is something that is horrendously difficult to understand and to implement and get correct. We don't even know if they are correct. And so I think it's better to hand that problem over to some theory people and say, okay, could you kindly prove that this algorithm is correct for us? And that will be one of these little building blocks that we'll use to build things. And then I would say to people, if possible, can you re-architect your system so you don't need, for example, leadership election or global memory? Quite often you can re-architect your problem such as you don't need to do that. So, for example, if my bank account details were held at me and not the bank, it would be much easier. It's the fact the bank is doing it and I can access it through different channels makes it insecure. So if you can change the architecture to, it's a kind of black magic. The magician has sort of done something, waved his hands and changed the problem slightly to make it one that's tractable. But yes, I mean...
So for these large-scale distributed systems, I've heard talks from people at Google describe the enormous number of different services they have interacting in order to answer a web query. So if they were building that in Erlang, do you think that would be particularly simpler?
No. No, it wouldn't.
See.
But you see, I think it would be simpler if Carl Hewitt gives a nice example. He said, well, if you have central servers and you ask them things, you leak a lot of information about yourself to them. So if you go to suppose I want to book an aircraft, or I'm going to go on holiday, so I want to book a hire car, a hotel, and an aircraft, and I go to some booking site and say, I want to book this aircraft. Trouble is, everybody's spying on me and listening to this, and advertising services are coming in. So when I go and try and buy a hire car, they already know that I do that, and they model their things according to that. Because as you do computations, you're leaking stuff all the time. So Carl Hewitt says it's much better to keep all the data yourself. And so if you want to book an aircraft, you could go to the 10 airlines that you're prepared to fly with and say, can you give me a little program that I can run on my computer whose validity is half an hour or 10 minutes, and you can run that locally, and then you can tell them, and you can get the hire car, and you get the hotels, and you can do all this. You don't leak any data. Nobody knows what you're doing. You're just requesting programs. So I think if you kept all your data to yourself, which you made the point in your lecture, if you have this single point where all your data is, it's much easier, and that single point should be you. Should be in your wristwatch or somewhere. You can have all your personal data there. You shouldn't put it in. You shouldn't let Apple or Google or anybody else own that, and you shouldn't let them provide all the services for you. You should define what the data is, and then you should get your software from different. There will still be this problem of how it interacts. It's not going to go away.
Those are essentially synchronization problems, but maybe we should let some other...
Yeah, we're getting into religious questions here. So you have a couple of questions on the screen. So on the left one, so what do you still what advantages do you still have if you put Erlang on a single shared memory machine, Linux machine?
What advantages do you get? Well, it's easier to program.
Say it again?
Easier to program.
Easy to program.
Yes.
But the failure is the same. I assume the
Yes,
question
yes,
implies.
yes. And then you can develop your... I mean, the nice way of developing programs, you develop it on one machine, and then you just deploy it on multiple machines. It will have the same semantics, only the message passing times with the latencies will change, but everything else will stay the same.
So what's your opinion about the enterprise bus architecture? Does it work the same way?
I think that's a marketing term rather than anything else. I've never really understood what enterprise bus architectures are. They show block diagrams like Peter's first diagram, which I've never really understood what they are. And I've never actually worked with an enterprise bus architecture, so I don't really know.
I have a question myself. So I know that you started peeing in your pants in the middle of the 80s.
I've never peed in my pants.
And it took a long time. It really took a long time before Erlang started to get adopted outside of the group. It was a big struggle. It was quite depressing at times. What was the big game change? Why did people suddenly start to use Erlang outside? Was it because this happened before multicore? It wasn't multicore that did that.
What started it outside was Ericsson banning it, because that led to it becoming open source. And when it became open source, it started spreading. So that was the main reason why it started. And then it's kind of picked up over the years. Usually it's been something like WhatsApp. I mean, WhatsApp it was written in Erlang by 12 inexperienced programmers. And they sold that company for $19 billion. And that gets a lot of positive publicity. There were some newspaper articles that saying that freelance Erlang programmers were the highest paid programmers in Silicon Valley. And it's that kind of stuff that causes it to spread. So it's positive publicity and things like that. It's always been a bit of an uphill struggle because you have to think slightly differently. Mm-hmm. And it's got a different syntax, and syntax worries a lot of people. So.
But also certainly multicores has helped a lot as well in the adoption, because this was a lot about scalability that you talked about here, right?
I don't know if it helped as such. I mean, it's all happening at the same time, so you can't really point to any... I think it was more the horizontal... I mean, we could scale out horizontally without multicores, and it was that kind of scalability that was first beneficial, I think. So, I mean, WhatsApp using sort of thousands of machines horizontal. It's that horizontal structure that they can build in a convenient manner that attracts them to it. Perhaps not so much the multicore bit as such.
Let's do one last question from the wall there. So, do Erlang programmers, do they have to manage starvation? Could they potentially create a starvation or deadlock problem?
Surprisingly, I mean, everybody said, well, can you prove the absence of deadlock or live lock and things like that? No, we can't, of course. Does it happen in practice? Often. I would say it's incredibly rare. It's just in practice, it happens surprisingly infrequently. And I think one of the reasons for that is that the libraries, there's some generic libraries which implement servers and decision tree, sort of supervision trees and things like that, are written in such a way that won't happen with them. You won't get deadlock and things like that with them.
Okay.
I mean, in theory it can happen. In practice, it doesn't happen much. And usually, if it does happen, it's easy. It's pretty obvious what's happened, and you can find out pretty quickly and fix it.
So I think we'll transition from questions over to lunch. Thank you much.
Thank you.